Hello and welcome to lessons 5.2 and 1.4, and this is part of Unit 3. Today we're going to look at relations and functions. So if we look at a set of ordered pairs, we can write ordered pairs in what we call set notation. So set notation essentially means that we have these curly brackets that are here on the end, and we put all of our ordered pairs then inside of the parentheses. So you can see that I have 1, 2, 3, 4 sets of ordered pairs or 4 sets of data. Okay, and again, we call this set notation. So what this allows us to do is it allows us to compare two different quantities. So if I wanted to write this data table here as a relation, I can do my set notation. So I'm going to put my bracket. Then I'm going to put my first data set, which would be right here. So I would have 18 and 4.25 to show my first point. Then my second data set is 20 and 4.40. My third data set would be 21 and 5.25. Then I would have 14 and 5, and finally I would have 18 and 4.85. And I'm going to put my bracket here in the end, and I can see that I have a set of my 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5 data points. Now when we look at functions, the definition of a function says that a relation that assigns exactly one output value for each input value. So what that means is that for every x value that you find, okay, there can only be one y value. If x has more than one y value, then we don't consider that relation a function. Okay, so what this means is if I have some x values, let's say, and some y values, and we'll just set up a table. Okay, so if I go -1, 0, and 1, okay, and then I go, we'll say 1, 2, 3, here, each x value has exactly one y, because -1 goes to just 1, 0 goes to 2, and 1 goes to 3. Now if I look at a different scenario, and I go, we'll say -1, 0, -1, and 1. And over here, I have 1, 2, 3, 4. Now notice, -1 goes to 1, 0 goes to 2, but I have another -1 that goes to 3. So I have two -1s, okay, but they each go to a different y value. So the definition of a function says for every x, there's exactly one y. Well, here I have two of the same x values, but they have different y values. So this here would be considered not a function. Okay? So we can use what we call mapping diagrams. And what a mapping diagram does is it lists our domain. Now, domain and range are two things that you're going to have to know. Domain are x values and ranges are y values. Okay, so the way I remember this is domain and range go with x and y. Now, if you think about it, alphabetically, D comes before R, just like X comes before Y. So domain and X values go together just like range and my Y values. So to create a mapping diagram, this is going to kind of help us see how many X values there are for, or how many Y values there are for every X value. We're going to use what we call a mapping diagram. And this just draws arrows from the domain values to our range values. So let's look at an example. So example 1 says, use mapping to determine if each relation is a function. So I'm going to create a table. Okay, and I have my domain or my x values, and I'm going to have my range, which is my y values. So when I look at my graph here, I have -4, which is this value. Then we have the number 3, which is right here. Then we have 8 and 9. And then we've already got number 3. So then if I look at my y values, we go from -2. Then I have, looks like I go 0, 1, 2, and 3. So how the mapping is going to work is we are actually going to map. So if I look at this coordinate point here, 3, -2, so 3 is going to go to -2. Then my 8, my point 8, 1, so 8 is going to go to 1. 9 is going to go to 2. Then 3 is going to go to 3, so that's going to go down here. And -4 is going to go to 0. So -4 to 0. Now, looking at this mapping diagram, I can see right away that this is not a function. Okay, and I can see that clearly because this number 3 here, actually, let's change our color. So 3 actually goes to 2 different y values. So because it goes to different y values, it tells me that this is not a function. Okay, or if you wanted to look at the next part, you can either map it out like this, or you can look and say, I have a 6.5, I have no other 6.5s. I have 1, 7, 1, 6, 1, 2, and 1, 5 for my x values. So you can map it out like what we just did over here. Or if you don't see a repeat in x values, then you can tell, like in this case, that this would be considered a function because there's only one x value for every y value. So, for example 2, if you want to, again, go ahead and try using the mapping, I would suggest that you do that. Otherwise, I can tell right away I have a -2 for an x here and a -2 there. So then when I go and I look at my y values, I have a -1 for a y and a 1 for y. So because I have 2 different y values for the same x value, I can see that this is not a function. And then for the second part here, I have 11, 12, 13, and 20. I've only got x values that are listed one time, therefore there's no chance for this to replicate or have different y values, so this here would be considered a function. Now when we're graphing, we have something called the vertical line test, or the VLT, and this is going to tell us whether or not a relation is a function. Okay, so how this works is if you draw a vertical line through a graph, and that vertical line touches more than one point, okay, then that tells us that it's not a function. If you can draw a vertical line through a graph and it only hits the graph at one point at any given time, then you have a function. So let's look and see how this is going to work. All right, for example 3, it says use the vertical line test to determine if each relation is a function. So if I graph the point 4, -2, 1, 2, 0, 1, and -2, 2, I get something that looks like this. Now, if I go and I draw a vertical line through each one of these points, okay, I do not hit another vertical line. So what that tells me then is that these points right here are functions. You can also confirm by saying I have a 4, a 1, a 0, and a -2. So my x values do not repeat. Therefore, there's only one y value for every x value. Now let's look at the case with the next set of data points. So if I include, we'll do these in red. So now if I only look at my red dots and I kind of ignore the blue dots, I can draw a vertical line through this point and only hit once. But once I go to draw a vertical line through my vertical axis here, notice that I end up hitting 2 dots, 2 red dots. So I have this red dot here, and I have this red dot here on my vertical line. So because I just hit 2 points on the same graph with my vertical line, this tells me that this is not a function. And you can come back here and confirm, because I have the point 0, 2 and 0, negative 3. I have the same x value, but two different y values. Therefore, this is not a function, and I do not even need to look at anything else. For example 4, it says use the vertical line test to determine if each relation is a function. Notice wherever I draw a vertical line here, I do not hit my graph in more than one spot. So I would say that this graph is a function. Here, as soon as I draw a vertical line, I hit two different points on that graph. So this here is not a function. And likewise, if I come over here to this graph, everywhere I can draw a vertical line, I only hit it once. So this graph here would be considered a function. Okay, for example 4, it says determine whether the relation 3, 0, negative 2, 1, 0, negative 1, negative 3, 2, and 3, 2 is a function. So if I graph these, this is what my graph is going to look like once I get my points on there. And again, if I go through and I draw vertical lines, notice so far nothing's happening, but once I get here, I draw a vertical line and I hit 2 points. So that tells me that this this relation is not a function. Now, when we're looking at relationships within our functions, we have two different types that we're going to look at. We have what we call our independent variable. So independent means that it does not rely on any other variable, and this would be considered our x values. Then we have the dependent variables, and dependent variables do rely on the value of the independent variable. This is our y value. So essentially your y value is going to depend on what you plug in for your x values. So when we look at independent and dependent variables, it says to identify the independent and dependent quantity in each situation. So for the first one, it says the amount of money earned babysitting increases with the number of hours spent. So I have my independent and my dependent variables. So you have to say what depends on what. And in this case, the amount of money is going to depend on the hours. So the amount of money, so maybe I'll say money, depends on the independent variable, which would be the hours babysitting. Okay, likewise for part B, it says the cost of the skating party increases with the number of people. So my cost is going to depend, so cost depends on the number of people, which is going to be my independent. Part C says the volume of water in a bathtub will decrease with the number of minutes that it has been running. So I'm going to put that the volume of water depends, okay, so that's my dependent variable. It's going to depend on the number of minutes. Oops, M-I-N. So number of minutes. Part D says the number of people attending the event decreases with the total cost. So number of people depends on the cost of your tickets. So the independent then would be the cost of the tickets. Now the last thing we're going to look at is called domain and range. So domain is going to be the possible values for the input or the independent variable. Or again, these are the x values. Our range is going to be the possible values of the output or the dependent variable, which again is our y values. So when we look at our next example, it says Maria earns $7 per hour for babysitting after school and on Saturday. She works no more than 16 hours a week. So we have to identify the independent and the dependent quantities. So her dependent is going to be the amount of money that she earns. So the money that she earns is going to depend on the hours that she works. So part B says find a reasonable domain and range. Okay, well, her domain says that she can work no more than 16 hours. So we can know that she can't work a negative amount of hours, so she has to work between 0 hours and 16 hours. And so that means that her range then is going to be, if she works 0 hours, she's going to earn $0. And I'm just going to put M for money earned. Now, if she works 16 hours and she's earning $7 an hour, if I multiply these two together, we can see that she's going to earn $112. So she can earn between $0 and $112 an hour a week if she works between 0 and 16 hours. Likewise, for our next example, it says Ken burns 425 calories per hour when he bikes. He bikes from 3 to 7 hours each weekend. We have to look for our independent and dependent quantities, and then we're going to find the reasonable domain and ranges. So the calories burned, okay, is going to depend. So calories burned depends on his time. So calories burned depends on the hours that are biked. So my domain then tells me that we are biking in between 3 and 7 hours. So I'm going to say 3 is less than or equal to H for hours, which is less than or equal to 7. And then the range then is going to be, I have to figure out how many calories he's burning per hour. So if he's burning 3, or if he's going 3 hours, he's burning 425 calories times 3 hours, which gives me 1,275 calories. I'll put a C for calories. And then if he goes 7 hours, we're going to take that 425, multiply it by 7, and we get 2,975. So he's going to burn anywhere between 1,275 calories and 2,975 calories. For our next example, it says you're going on vacation and you plan to go for 4 to 10 days. The hotel costs $125 per night. We're looking for independent, dependent variables and our domain and range. So the way I look at this is your hotel cost is going to depend. So hotel costs are going to depend on your number of days that you are gone. So our domain then, the days that are gone tells us that we're going to be gone between 4 and 10 days. So we have 4 is less than or equal to the number of days that we're gone. And that's less than or equal to 10 because we're gone between 4 and 10 days. Now, if we're gone for 4 days and our hotel is $125 a night, I'm going to multiply that and we get $500. So we have $500 is less than or equal to our cost, which could be less than or equal to $125 a night times $10 is going to be $1,250. So we're looking at spending anywhere between $500 and $1,250. Now the very last thing that we're going to look at in this section is called a function rule. So a function rule is an equation that describes a functional relationship. Okay, and a lot of times function notation is going to look like this. It will say f of x, that's how we read it. So it says f of x equals, and you might have something that says x plus 1, let's say. Okay, so this just tells us that we have a function. That's what the f of x means. And right here is our actual, like our function relationship. Okay, now this x right here, if we want to evaluate it at a specific value, then we can plug in a number. So I could rewrite this. If I wanted to evaluate this function, let's say at f of 1, then what that tells me then is wherever I had an x, so like right here, I'm going to replace that x with a 1, and I really end up with 1 plus 1. So I would say that that then is going to equal 2. So f of 1 equals 2. And I got that literally from plugging in this x into this x right here. So if I look at this example over here, it says evaluate f of x equals 2x minus 1 when f of 3. So this tells me I'm going to plug in a 3 for this x. So I have 2 times 3 minus 1, which gives me 6 minus 1, or 5. So this is just a nice quick way to tell us how to evaluate a function at a very specific point. So our second to last example says make a table for f of n equals negative 2n squared plus 7. And it says use 1, 2, 3, and 4 as our domain values. Remember, our domain is our x, and our range is our y. So I have 1, 2, 3, and 4. So now what I'm going to do is I'm going to find f of 1, which really means that I have negative 2 times 1 squared plus 7. So 1 squared is 1 times a negative 2, so I have negative 2 plus 7, or negative 9. Oops, sorry, that's a positive 5. So when I plug in a 1, I end up with a positive 5. If I evaluate f of 2 means I have a negative 2 times 2 squared plus 7. 2 squared is 4 times a negative 2, so I have negative 8 plus 7, which gives me a negative 1. Then I'm going to do the same thing with a 3. So f of 3 equals negative 2 times 3 squared plus 7. 3 squared is 9 times a negative 2. So this gives me a negative 18 plus 7, or a negative 11. Likewise, if I plug in a 4, 4 squared is going to give me 16 times a negative 2, will give me a negative 32 plus 7, so I get a negative 25. So this right here is my table when I use 1, 2, 3, and 4 as my domain values. Likewise, for this next part, I'm going to make a table for y equals 8 minus 3x, again using the same values of 1, 2, 3, and 4. So x is 1, 2, 3, and 4. And my y values. So if I plug in a 1, I have 8 minus 3 times 1, or 8 minus 3 is 5. If I plug in a 2, I have 8 minus 3 times 2, or 8 minus 6, which is 2. If I plug in a 3, I have 8 minus 3 times 3, or 8 minus 9, so I get a negative 1. And when I plug in a 4, I have 8 minus 3 times 4, or I end up with a negative 4. So my last example says, evaluate the function rule f of a equals negative 3a plus 5 to find the range of the function for the domain. So if my domain is negative 3, 1, and 4, I'm going to plug in my x values, my y values. I have negative 3, 1, and 4. And if I plug in a negative 3, I end up with negative 3 times negative 3 plus 5. Negative 3 times negative 3 is 9. 9 plus 5 is going to give me 14. If I plug a 1 in for a, I have negative 3 times 1, which is a negative 3 plus 5, or a positive 2. And if I plug in a 4, I have negative 3 times 4, gives me a negative 12 plus 5, which would give me a negative 7. So my range is going to be just my y values, which I get from over here. So I end up with 14, 2, and negative 7. So now I'm going to do the same thing. It says find the range of each function for the domain -2, 0, and 5. So if you want to, I personally think the table is probably the easiest way. So I have -2, 0, and 5. So -2 minus 6 will give me a -8. 0 minus 6 is a -6. And 5 minus 6 is a -1. Likewise, if I do my XY table here, I have -2, 0, and 5 are my X values. -4 times -2 gives me a +8. -4 times 0 is 0, and -4 times 5 is a -20. And my last one, if I do my XY table or my domain and range, and I have -2, 0, and 5. -2 squared is 4 plus 1 will give me 5. 0 squared is still 0 plus 1 is 1. And 5 squared is 25 plus 1 gives me 26. So this does conclude our 5-2 video. Please let me know if you have any questions. Otherwise, have a great day.